wireless networks or Wi-Fi. Sometimes people also call it as wireless fidelity. But here the 802.11 is the IEEE. Wi-Fi is the formal name. Now Wi-Fi is using those spectrum which are unlicensed. Most of the frequencies which we see are licensed by the government, with the mobile cellular the network also use. But here the Wi-Fi is using the unlicensed band, and this has been given to ISM. ISM this for industries, as for scientific, and for medical usage, for research purposes. For these three different, because government cannot sell this to these also ISM. So ITUR has bands 902 to 928, that is for industry, and 2.4 to 2.5 gigahertz is for scientific usage. And these are free band, unlicensed band. We can use it if you are working in any of these fields. 5.725 to 5.825 gigahertz. This is for medical. So these are reserved unlicensed band. Wi-Fi is using this. So 802.11, they have clients. This can be your mobile phone, this can be your laptop, and the infrastructure, that is we have access points, or we already know it by the name of base station. And since Wi-Fi has a range, so it is installed in a building, an area, a range, and these access points, see, the laptop and the mobile phones are wirelessly connected to access points, but these access points are connected through wire. They are wired connected. So there is a backbone of wired network. And these clients, they are talking to access points. So the systems have to go through access point, then only they can talk. But there are certain ad hoc networks like MANET, etc. If they are in same radio range, they can talk directly without an access point. This is also possible. Now when we are dealing with the wireless networks, the frequency which we use in 802.11, these are radio signals. Now sometimes they can be reflected off the solid objects, which is the objects which we find generally as infrastructure, the buildings, etc. And because of this, the multiple echoes of transmission, they may reach a receiver along different path. So this different path, for example, one may reinforce. Two signals may reinforce, or the two signals, they are coming out of phase, so they may cancel each other. So this kind of phenomena of cancelling is called as multipath fading, and this is very natural, and most of the design issues are along this with this discussion only. So if you see here, if some reinforcement is there, you will get a non-faded signal and even higher. But if it is cancelling, the two signals are cancelling each other, you will get a faded signal. So what is the solution? Path diversity is the solution. So this has come to overcome the variable wireless condition. So we can take different multiple independent paths to send the information, not sending in one direction, but different paths. That is why it is called path diversity. And the information shall be received even if one of the path is giving you a faded signal. So the initial 1997 I'm talking about standard, this defined a wireless LAN that was running at 1 megabit per second and 2 megabit per second. And this was using frequency hopping. That is, it hops, it changes the frequency. One frequency it is working, then another frequency, then third frequency. So this was frequency hopping going on, and using the SPED spectrum. That is the whole of the spectrum which is being assigned. Whole of the spectrum is being used. Okay, spreading the signal across the allowed spectrum. This was 1997. Now the technology emancipated. So the SPED spectrum design, it was even more extended, and it became the 802.11b standard in 1999, and the data rate increased 11 Mbps, then 802.11a, then 802.11g. These standards, there was a new modulation scheme they adopted, and we'll be talking about this OFDM, which is actually orthogonal frequency division multiplexing. And this OFDM is what? To just give you a hint, this is all about slicing. That is, it divides a wide band of spectrum into very short and very narrow slices. Over these slices, different bits are sent in parallel. So this is how the frequency selective fading is less. So this becomes less sensitive to the frequency selective fading. This is the picture I wanted to highlight. We'll be talking about this in detail. And there are different versions giving different speeds. So we have AG, AC, AD, and this AD I'm talking about because it will work only in the indoors because it cannot penetrate the wall. Okay, so we will have the extension and the extender kind of thing. But here you see IEEE standards are there, 802.11a and 5411b 11 Mbps. These are the data rates. G 54 Mbps and 600 Mbps, AC 1.3 Gbps, and then we have AX 10 to 12 Gbps. And you mark the frequency range 2.4 gigahertz until 5 gigahertz. Now, since the wireless is a broadcast medium, it goes to everyone. So 802.11 has to deal with a collision problem. Because collision means two packets can collide. So in order to handle this, 802.11 also uses CSMA, carrier sense multiple access. And this CSMA, you see here, this is the classic wired Ethernet. It was used in classic wired Ethernet, 802.3. And then came the Aloha. So this CSMA and Aloha, actually the collision detection and avoidance scheme is taken from them. So here, very simple algorithm, computer or the computing device wait for a short random interval before transmitting. And if someone is transmitting at that time, it will again wait for the next transmission. And this scheme really worked well in the wireless environment, Wi-Fi environment. It was not working that well in the wired networks. I'll give you a scenario here. How does it work? See. Suppose this computer A is transmitting to computer B, but the range of A and C is not there. That is, the radio range of A transmitter is too short to reach computer C. Now, if C wants to transmit to B, it can listen that if someone else is transmitting, but as you see in the picture, A and C cannot talk. They don't know about each other. But if C starts transmitting, and you know already A has started transmitting, there will be collision. So once this collision happens, what will happen? C has started sending, A was already sending. Because A and C are not in range, there will be collision. What is the solution? Here, the sender will wait for a random time, and it will retransmit the packet. In Wi-Fi, there is another challenge which is called as mobility. Once you hand off, that is, if the mobile client, a mobile phone or a laptop, it is moving from the access point, it has to hand it off to the next AP, that is access point. For example, you have a house. If you go to a certain place where there is no signal, what will you do? Then you can use the extender or you can say the booster. So the solution is that it can consist, the network 802.11 can have multiple cells with multiple APs. There is one more issue, that is the security in the broadcast wireless transmission. Because, we have we don't want it to be received by anyone else. So 802.11 standard has included, is there encryption. If you are sending AB, make it as XY. When it reaches to the sender, it can be decrypted to AB. AB is sent, making it as XY. That is the basic idea of encryption. So WEP was very popular, wired equivalence privacy. But finally this was broken because it was the encryption technique. And then came the in the 802.11i, it was replaced by Wi-Fi protected access. Initially, it was called as WPA, Wi-Fi protected access, but now it has changed to WPA2. WPA2. These are the encryption techniques. There is one more, authentication also there. So in 802.1x, here we have the certificate-based authentication for the access point. Client has to take the authentication, then only will be able to access the Wi-Fi or wireless network. So mobility and security are also the issues in wireless transmission.